Thank you everyone for coming. First of all, I'd like to begin by our acknowledgement of country. I would like to acknowledge the traditional owners of Australia and recognising their continual connection to land, water and culture. I'm currently in the lands of the Wangal people of the Eora Nation and pay my respects to their elders past, present and emerging. I further acknowledge the traditional owners on the countries in which you are on and pay my respects to their elders past, present and emerging. I would like to welcome everybody to the Sydney Nano Meet the Author seminar series. This is run by the Early Career Research Ambassador Program within Sydney Nano. This seminar series aims to showcase and highlight the amazing work that's done within our Sydney Nano community. And it's an opportunity for a speaker to talk about themselves, their journey, and also their work. And I'd like to hand over Moritz to introduce Hansheng.
Yeah, hello everyone, and thanks for joining this seminar. So my name is Moritz Merklein. I'm a research fellow here at the School of Physics, working in the Acknowledgment Research Group in Optics and Photonics. And together with Nick, I'm chairing this session today. And it's my great pleasure to introduce to you Dr. Hansheng Chen. He won our Sydney Nano Publication Award in 2020. So currently he's an engineering research assistant at the School of Aerospace, Mechanical and Mechatronic Engineering at the Faculty of Engineering and Information Technology at the University of Sydney. Hansheng completed his PhD in 2019 in the School of Physics here at the University of Sydney. He was supervised by Professor Rongkun Sheng and Professor Simon Ringer. And his expertise is in structural and compositional analysis of various materials using advanced microscopy techniques. So today's talk is about bridging microstructure and magnetic properties of rare earth permanent magnets. So take it away, Hansheng.
Thank you, Maurice, for the introduction. And thank you everyone for joining, especially in this slightly difficult time. My name is Hansheng Chen. I'm currently an engineering research assistant in AMME in Simon Ringer's group. Today, I would like to introduce a very brief introduction on how to bridge the microstructure and the magnetic properties of the permanent magnets. And before that, just let me introduce myself a bit. I was born in Shenyang, China, a beautiful central city in the northeast China, you can see here. And it has a population of 7.6 million, and it has a well-known called Mukden Palace, which forms as the palace for the emperor at the beginning of the Qing dynasty in China. And on the bottom right is actually the beautiful night view of Shenyang when you actually arrive at the airport, and when you either by taxi or by car, you can definitely pass through this river and the bridge and to enjoy the view. And welcome to my hometown Shenyang for the tourism. And I got my bachelor degree in Tianjin University in 2014. The former name is called Peiyang Uni, and it's actually the first modern higher education institution in China, and established in 1895. And it's both the Project 211 and Project 985. And when I was at the fourth year, I got a project accomplished under the supervision with Professor Wen Bomi. And after that, I was very fortunate to get the opportunity to study my PhD in the School of Physics, Faculty of Science, University of Sydney, a beautiful city here. And under the supervision with Rongkun and Simon. Until I got my PhD degree in 2019. And after that, I got engineering research assistant job in further Simon's group and the AMME. Currently, I was mainly involved in the called Auxiliary project, which you can refer more information in the web address here. And recently, we got a few interesting works get published, which mainly on the additive manufactured Ti6 for titanium alloys, the Inconel 73A, nickel-based alloys, and also the hydrogen alloys. And my expertise will covers more from the functional magnet materials, but also the digital manufactured metals, and majorly focus on the characterization works by the microscopy using a typical variety of the microscopes listed on the right above. And today I'd like to mainly show my PhD work, which mainly on the functional magnetic materials. And before doing that, I would like to acknowledge a few people and also the facilities and the foundings, and especially for the facilities, the Microscopy Australia and the Australian Centre for Microscopy and Microanalysis, ACMM, which I conducted most of the experiments in. And also for the founding, I would like to thank the AIMS Postgraduate Top-Up Scholarship, which is now named as the Sydney Nano Institute. And also the collaborators in China, DMEGC, CISRI, and also Beijing University of Technology. Okay, and let's begin from the challenge of the permanent magnets. We know that quietly the energy consumption has become a severe issue, especially first is the pollution. You can see on the left, you can barely see the Beijing Forbidden City in some of the days in China. And also on the right hand, you can see the increasing demand of the renewable energies. For example, the wind energy, solar energies here in recent years in Australia. And besides that, also the hybrid of electrical vehicles like Tesla or has attracts a field attention here. And the permanent magnets have been applied widely, not only in the daily life, like the wind turbines, the electrical motors, bicycles, the hard disk drives, the MRI, and also it can be applied in the communication for the satellites, for the national defense. And in 40 years, from 1960 and the 2000, you can see a huge bump for the development of the magnets. And before 1960s, called the maximum energy product, which means the magnetic energy, how much energy that can be stored in the magnet is quite low. You can see it's just around 1 or 2 Gauss Oster. Majorly the material will be the ferrite, but yeah, some brilliant researchers just found whether they can use some like cobalt or the iron, and also like nickel, because they all are ferromagnetic elements, whether they can use them as a base, and whether they can add some rare earth elements, some like samarium here, and also the neodymium to further enhance the magnetic properties. And from them, they actually fabricate the samarium cobalt based 2 kind of generations rare earth permanent magnets. But the issue is still here. You can see the maximum energy product is only around 30 or 40 mega Oster. And in 1984, the Sagawa from Japan, and also simultaneously the GE company in the US, they both fabricate the higher energy magnets based on using the neodymium, iron, and boron, which is called the 3rd generation of the rare earth magnets. Even in today, especially the 2nd and the 3rd, they have still attract mostly attraction in the community. And in the community, our mission is to majorly to do two things. And what you can see here is a typical hysteresis loop with the applied field on the x-axis and the magnetization on the y-axis. And the first important point is point C. which is called the Random Magnetization, which represents how much energy it left when you apply a negative 4, when the H equals to 0. And it actually strongly affects the magnet energy stored in the magnet. So the higher this point, the magnet will be lighter, will be smaller. And the other important point is point D, which is called the coercitivity. That actually presents how strong the magnet can exert in the demagnetization field. If the coercitivity is higher, then the magnet can be working in much severe conditions, such as higher working temperature or even lower working temperatures. So what we would like to do is actually to make this point higher, to make the D a bit far from the original point. And to do that, we can't avoid one point is to attune or to tailor the microstructure of the magnets, because especially the coercitivity is quite relevant to the microstructure. And previous research has worked on using broad microscopies to look at the microstructures from the microscale to the nanoscale, or even atomic scale, and to get the microstructure, to get a composition, to get the defects, to get different phase fraction here. And the way they like to correlate the microstructure and the magnetic properties is to using micromagnetic simulations. But the quantification here is not that, actually it's not that quantified, because they usually using the default values as an input for their micromagnetic simulations. They didn't consider, even they have some features, they have some information here, but they didn't put that, transform the observations into the information as the input for their simulations. So the aim of this work, actually for my PhD work, is actually to bridge the microstructure and the magnetic properties based on, to dig some more information from the observations what we have. For example, here from the atom probe tomography results. And I would like to introduce this one in the next slide. And this, yeah, like I mentioned before, the standard approach is using the default values as an input, but we actually advanced slightly to build up a more accurate microstructure feature-based simulation models. And atom probe tomography is actually a very high sensitive destructive techniques in measuring the composition and also the position of the atoms with sub-nanoscale spatial resolution. The principle is here, and the samples actually made into a really fine needles with a radius of around 50 to 100 nanometers. And typically it's metals because it's conductive, but recently it can be applied into semiconductor and also even biomaterials like steels, tools. When we put the sample here, we applied actually a voltage pulsing field between the samples and called the local electrode. And yeah, sometimes we add the laser just to assist the atom evaporations. Yeah, that's, I think, very great, excellent for the bio and semiconductor materials. And the atoms will fly and then detected by the PSD detector. Based on the time of flight, because each element, they will fly in different time, then we can calculate, get the chemical identity. And based on the position of the hit in XY, we can go the XY coordinate. Because the experiment is a destructive experiment, the atoms will evaporate in sequence. Based on the sequence, we can determine the Z coordinate. And then based on XYZ, we got the 3D reconstruction later, and also with the chemical identity here. And next, I would like to show how I bridge the microstructure by majorly the atom probe tomography and with the magnetic properties simulated by the micromagnetic simulations in these three type of magnets, which is the sintered Neodymium Ironborn magnets and the second generation ceramic cobalt based magnets, and also a recent called this Neodymium ceramic Ironborn magnets. The ceramic is quite cheap, but how but the intrinsic property is not that good. But how we like using a new alloying technique, not the alloying, the fabricating technique called dual phase technique to enhance the properties here. And for the sintered Neodymium Ironborn permanent magnets, you can see the structure is something look at similar is like this, and the magnet is composed of majorly like two phase. One is the gray part here called the matrix phase, which is 214-1 phase here, and the brighter phase is the rare earth rich phase, and also with some grain boundaries highlighted by the black angles. And the coercitivities in this type of permanent magnets is basically determined by the nucleation on the defect, especially the defect between these at this interface between these two phases, and also on the grain boundaries here. So we would like to quantify the directly the coercitivities with the defects here. And we get some great atom probe data set, and we can see the grain boundary here. You can see the grain bar. Actually, the iron compositions is not uniform along the grain boundary, and we by extract the values, the composition from the atom probe results here, and we construct the mathematical models by fitting some original published data sets in some other previous works. Based on our composition, we determine the three default values for as the input for the micromagnetic simulations. And then we got a simulated intrinsic coercitivity. And what we found interesting here is you can see here, even, okay, let's say the iron concentration is the same in like at the grain boundary, but if your grain boundary is not homogeneous along, if the iron distribution is not uniform along the grain boundary, you can see the coercitivity is quite lower than actually a homogeneous grain boundary, which is around 27% lower. This is actually quite interesting, and then will form some guidelines, will form some for the manufacturers to say how to more accurately control the, especially the ferromagnetic distributions at the grain boundaries. And except the grain boundary composition, the grain boundary thickness also is a very important factor affecting the coercitivity. And yeah, the same, we can see the grain boundary actually not uniform in the thickness, varies from 6 nanometer and to 15 nanometer. And based on the simulation, we can know that, okay, if the grain boundary is thicker enough, about 15 nanometer, the coercitivity is actually reached to a plateau. But if it's thinner, then that would actually strongly rely on the different concentration of iron, and the reduction will show different behavior here. And also the third important factor is not only the grain boundary, but also the neighboring matrix grains. The this neodymium iron magnet is actually all one strong texture for remaining high remnant magnetization. So the red grains here is all one strong texture, you can see, but you can see some yellow one and some pink one here, which is we call the misaligned, because it's somehow derailed from the all one directions here. And actually the grains, the adjacent grain boundary, whether it's ferromagnetic or non-ferromagnetic, magnetic will strongly affects the nucleation field at here, which you can see on the right side. And for the second part, for the samarium cobalt type magnets, it's actually a totally different type of permanent magnets. The coercitivity here is majorly governed by called domain wall pinning, which you can see the different, like the cell boundary here. When the domain actually wanted to penetrate, go through this part, it actually pin on this boundary on some feature. And the pinning force here is actually is proportional to the coercitivity. And the what we do here is we add some more copper fine particles in the base magnet, because what we target is to increase the copper concentration in the 1,5 phase here. And and again, by using the atom probe tomography, we can identify the different concentration of the constitutive phase in the pure magnet and also with the copper alloyed magnet. Okay, it should be mentioned that the previous pure magnet, there also copper here, but we just add some more copper in the system, and we can directly see the copper enhanced a lot in the 1,5, just a typical phase here. You can see like a rate, the maximum ratio around 40 atom percent compared with the 30 atom percent for the pure magnet. But we actually observed the copper concentration vary along in different 1,5 cell boundary phase. And then we do the statistics and then grab the information more statistically. We got the distribution of the maximum copper concentrations in this phase. And using that values, we construct the models. You can see this one, the models here. The blue is the 1,5 phase, and the thickness, we're varying the thickness, and also we're varying the concentration here. Based on different concentration, we again simulate the K1 MS and the exchange coupling constant based on our atom probe results here. And we get the simulation results. The newly copper alloyed magnets, the coercivity can reach to around 27 kiloholster, which is almost double than the pure one, which is, you can see, is quite consistent with our experimental results here, the 27 kiloholster for the copper alloyed magnet. And then we compare different microstructures we found. Firstly, the 1,5 cell boundary phase become more continuous, but also the copper elements actually diffuse from the grain boundaries, which is serves as a diffusion path and to these 1,5 cell boundary phase. Then the copper concentration becomes higher, which pose a more higher pinning force for the magnetic domain motion. That's the reason for the coercivity enhancement. For the final one, the neodymium ceramium Ironborn magnet. Actually, I missed some slide. just here. Yeah, the ceramic is actually abundant in the earth, but also very cheap. You can see it's quite 20 times cheaper than the neodymium actually. So there's actually more ceramic in this world than neodymium. But the reason is, you can see once, if you're using the ceramium as the base for these two 14-1 phase, the anisotropy field actually directly related to the intrinsic coercitivity is half. Then we would like to balance the incorporation of the ceramium here. And one previous technique called dual phase is by constructing a so-called co-shell structure, which can majorly enhance the nucleation field at especially the interface here. And here we would like to dig more on how the microstructure looks like in this dual phase permanent magnet. And then we can see the manufacturing. We prepare some 0 ceramium and some also 50 ceramium here. And with the mixing ratio between 2 to 3, adding them together, and after the typical HD hydrogen decryption and the jet milling, and after pressing these magnetic powders together and then sintering, we got called DMDS in sintered sample. And then we can know that the average ceramic concentration here is 20%. 20 here means 20, the ceramium takes up 20% of the total rare earth elements. Because as a comparison, we fabricate the single main phase as a comparison. And then we can see at the micro scale, we can see the ceramium here. We can see the not like that typical core shell, but a not uniform distribution of the ceramium in the matrix phase here. And when we're using the atom probe tomography, we can know that beside this green boundary, you can see the 1, 2, 3, 4, 5, 6, that's in 2 different neighboring grains. And for the 1, 2, 3, the ceramium is actually remain at a low constant. But for the bottom here, we can see a enhancement of the ceramium concentration, which led by these dual main phase techniques. Sorry, I forgot to mention, because the point of this work is actually we found the coercitivity of this dual main phase, multi-main phase magnets actually be higher than the SMFP here. But even with little sacrifice of the remnants and the BH, the magnetic energy, maximum magnetic energy. And when we dig through, we found a newly type of the grain boundary, which majorly enhanced with ceramium here. And also you can see there's some interesting segregation on this interface, like the copper here, you can see copper mostly segregate on the interface between the matrix phase and the grain boundary phase. And that's the like the merit of the atom probe. You can know where the atoms exactly where. And the other merit of the atom probe is the cluster analysis. We do 3 types of analysis in this sample. We first can see the ceramium-rich clusters at the green boundary phase. And we can also see some copper-rich clusters at the interface here between the matrix and the one type of rare earth-rich phase. But there's no gallium-rich clusters here. And finally, we compare the microstructure of our asinter MMP, neodymium ceramium Ironborn magnets compared with the asinter ceramium 0 magnet and also ceramic containing, but manufactured by the SMMP. First we got some cold shell structures, but in some of grain it's not that uniform distributed. That's the actually like one future direction, how we can more accurate, more tune the core shell structure here. Besides that, we did observe some ceramium rich phase, which marked by black here, and also some clusters with ceramium with copper, but no gallium clusters. And for the future directions, first, this type of microstructure feature-based micromagnetic simulations can be applied not only in this a few type of magnets, but also can be exchanged more on not the permanent magnets, but also soft magnets. But here, yeah, I mentioned the aluminum, nickel, cobalt would be a great candidate for this one. And also, yeah, there's some new attempt on the additive manufacturing of the permanent magnets, especially there's some work on the PLBF, the powder laser belt fusion, and also some DED, directly energy deposition technique. But I think there's the microstructure is not, it's not easy to be controlled because there's some like steep thermal gradient, also the thermal durations in the during the rapid heating cooling process. So it's really hard to control that one. And also the third one is because most of the simulations I'm working on is like 1 or 2 grains there, but the multi-grain based micromagnetic simulations will be strongly required. Yeah, for the conclusions, we use the powerful atomic scale, the atom probe tomography, which can quantitatively measure the composition of the constitutive phase, also the segregation behavior in different type of magnets. And also we, based on the experimental observations, we estimate three strong factory parameters: saturation magnetization, anisotropy constant, and the exchange stiffness. Yeah, exchange coupling stiffness. And using the parameters here, we construct the models for the simulation to quantify, to bridge the microstructure and the magnetic properties of the permanent magnets. Thank you for listening, and yeah, just welcome for any suggestions, any queries, yeah, any questions.
Awesome. Thank you, Hansheng. That was fantastic.
Thank you.
I would invite anybody to either type questions in the chat or feel free to unmute yourself and ask any questions. While we wait, I could probably start then. And Maritz, feel free to jump in at any time if you do like. One of the kind of really simple questions I had, and you kind of pointed it out at the future direction slide, is if you're going to have multiple grain structures, is there too many grain structures you can have where this will start having a detrimental effect?
Actually, yeah, I think that depends on the first computational power. Currently, so far as I know, the simulations, micromagnetic simulations of FEM, finite element simulation. So yeah, great. Yeah, the the more grains, I think the result will be accurate. But that also depends on the mesh size and how the resolution here. But also, yeah, as I mentioned, because it's not just the mesh grain, but there's also some microstructure type of features. Why that you include them? Because typically they, the researchers, they include the grain boundaries, like what I observed before, as just a non-magnetic phase. For example, the three here, for example, if it's a non-magnetic phase, the magnetization here will be 0. And then I think the exchange stiffness will be at 0 as well. but it's actually not correct because there's still some ferromagnetic elements like iron, cobalt there. Yeah. So yeah, based on your question, yeah, I think need to cooperate more grains, but also to consider the microstructure features.
Another question I had was with your addition of copper, you did have a thickening of the grain, and it shifted your, I'm not quite sure what the curve's called. I think it's 1 or 2 slides below, but it shifted it, that one, in the experimental results in the bottom right, it shifted it left. Was that so you could then use it at a different temperature?
Yes, right. The higher this one, then you can, then it shows more strong capacity for the DMAG. Then you can apply like 200 Celsius degree, yeah. And also that's the merit of the ceramic cobalt one, yeah, for this type of magnets, yeah.
That's a fantastic result. How, I mean, is it completely reproducible just based on the method that you have, or is there some variability that you always can get when formulating these materials?
Actually, the value here, it varies because you can, there's a few variables in the simulations. First is the thickness of the 1,5 boundary here, and also the gradient here. Actually, the gradient here, you can see the slope, whether it's like steep or it's like slow slope, a smaller slope here, will actually affect the properties here. But we found that it's just there, but yeah, with like a certain deviation, yeah.
Fantastic. There was one last question I did have. I'm not quite sure if it's possible or not, but are you able to monitor these materials in real time under stressful conditions and see if your material does change or how effective it can be?
You mean stress under stress condition?
Yeah.
Chemical stress or?
I was just wondering if you can in its application setting. So if you are using it under really high temperature, can you do the image, your micro imaging at that temperature and see what happens?
I think that it's applicable because, but mostly in the TEM, there's one called in-situ TEM. You can imaging the microstructure evolution with heating temperature in the TEM system as well. Yeah. So yeah, I think principle is feasible. Yeah, but the TEM actually transmission electron microscopy using really high voltage electron beam. So the magnetic material is not that applicable in the TEM. Yeah. So
I don't think they want you to heat that up too much. They spend too much time putting all the liquid nitrogen in.
That's true, yeah. But for the applicable, yeah, I'm not sure. Yeah, if in the industry, they can monitor. Yeah, it should be, yeah.
An interesting question, I think, to then just see what actually happens when it demagnetizes or when it just, is that well understood?
Yeah, that's in some called Lorentz TM, they actually apply the field, magnetic field, yeah, external field in the TM, yeah. And then they observe the domain, like movement.
Okay.
Yeah.
Yeah, very interesting. Are there any more questions from the audience, maybe? Otherwise, maybe I ask a follow-up question to what you said about the simulations before, if it's a finite element. And of course, you have then the problem that you want to model the microstructure, so you need a very fine mesh, but then you need a certain size to get all the boundaries as well in, and you have these much bigger domains. So that fundamentally, it's very hard to break down the problem into smaller chunks. So how much computational power would you actually need to have a realistic model? Is that something that can be run on a current supercomputer, or is it still too intensive model a realistic system.
And yeah, thanks, Morris. Yeah, I think you're absolutely right. Because for my PhD, I only work on, like, for example, the here is 100 nanometer, and the mesh size is 1 nanometer, and that can be run in the just the desktop for,
Okay.
I think probably half day for one data set. Yeah, depends on how difficult, how complex the structure here. But yeah, if multi-grains incorporate with like different like features there, that absolutely need more time to calculate. Yeah, will be. Yeah, I think supercomputer would be a choice. Yeah, would be a solution for that.
All right.
We don't seem to have any questions left in the chat. Well, if there are no more questions, can we please all thank Hansheng for a fantastic presentation? And I'd like to thank you all for participating in this session today.
Yeah,
Thank you, Hansheng.
Thank you, Nick.
Thank you.